I would like to thank Andrew and Kilian for the invitation. It's a pleasure to be here with you. So I'm going to talk about the elephant random walks and some connection with the Pitman-Ewens process. So all will be clear very short. So you can stop me at any moment if you have questions. So I will introduce the elephant random walk, the elephant random walk with stops, then the Mittag-Leffler distributions, some results on the elephant random walk with stops. I will try to prove a lemma which is a keystone of all the results here, and then I will switch to the Ewens-Pitman process, also known as the Chinese restaurant process. Okay, so about the elephant random walk. The elephant random walk was proposed in 2004 by two physicists, Schultz and Timper, and they want to find a random walk depending on a parameter such that you switch from diffusive regime to a super diffusion regime depending on the parameter you have. They call it elephant random walk because it's a random walk which knows all how can I say that? She knows all the history of where it has been before. So the elephants start at the origin. It goes to 1 or to -1 with probability S or 1 minus S. Then we have three possibilities. It goes to the right with probability P, to the left with probability Q, and stay in the same position with probability R. For the standard elephant random walk, the elephants always move to the right or to the left. Here, it can stay on its own position, and it will be more complicated than for the elephant random walk without stops. So at time 1, we do this. At time 2, what are we doing? At time 2, we choose the site where we have been before, and it was times 1. So we make the same move as the one we have done for time 1 with probability P. We move to the other position with probability Q and stay with probability R. So it will be clear. So all the move will depend on the past. Why? Because of this. At time n, what doing the elephant? You took an integer k uniformly chosen among the previous time, 1 to n, and you make the same move as the one you have done at time k with probability p, the opposite move with probability q, and you stay on your own position with probability r. That is the reason why the elephant random walk, you also will, all this random walk will depend on all the previous past steps. And so we're interested in the position of the elephant random walk with stop, denoted by Sn. Do you have questions? Is it clear or not? Okay. So in contrast with the standard random walk, you pick k between 1 and n uniformly. And this is really different from the standard random walk. Okay. A second, oh, sorry. Where can I put, I don't know how it works. Okay. Another quantity really of interest is the number of ones, or you can see that at the number of moves of the elephant. So the number of ones I denoted by sigma n. For the standard elephant random walk, xn square is always 1 because you move to the right or to the left. So xn square will be always 1 and sigma n will be n. Here, it's different because you can stay to your own position. And it will be much more complicated to study the elephant random walk with stop because of that. So I can explain you this in details. It's very easy. The conditional expectation of xn plus 1 given the past up to fn is sigma of x1 to xn. So the conditional of expectation is what? You have, you can see xn as alpha n plus 1 x u n plus 1 given the path, where un is uniformly distributed over 1 n. And alpha n plus 1 is 1 with probability p, minus 1 with probability q, and 0 with probability r. So it is easy to see from this, alpha n plus 1 is independent of x1, xn, and un plus 1. So you can see this as the expectation of alpha n plus 1 times this term. So the expectation is p minus q. And this term is simply 1 over n, the sum from 1 to n of xk. So this is directly a Sn over n, where a is an important parameter is p minus q. So very easy computation. It's very clear. The xn square, you can do the same. I put a square. So it will be, yes, I have to explain. No, it's not totally the same. Xn square, if we go back, xn plus 1 square, it's xk square with probability p plus q and 0 otherwise. So the conditional expectation of this guy, same calculation will give you b sigma n over n, where b is p plus q. Okay. Okay, so we have two parameters which are very important. They are A and B. And what is important here to see is the following. Xn plus 1 square, it's xk square with probability P plus Q. So I will, okay. The very important thing here the two parameters first, A B minus 2, B. And the conditional distribution of xn plus 1 square given the past is a Bernoulli distribution with parameter Pn, where Pn is simply B sigma n over n. And we will see later for the Ewens-Pitman process, we will have a similar thing. Do you have questions? No? Okay. So trajectory of the elephant random walk with stops. So we can see stops here. We can see stops where it doesn't move. So we have three regimes. The diffusive regime, where P is smaller than 3/4 times 1 minus R. This is a diffusive regime. When R is equal to 0, we find the critical value 3/4, so it's normal. The critical regime, when P is 3/4 times 1 minus R, and the diffusive regime, the superdiffusive regime, sorry. So in the two first situations, we are very close to the origin. The random walk is not going to infinity very fast. It's close to the origin. And in the superdiffusive regime, it goes to one direction very fast. Okay. So to study the asymptotic behavior of the elephant random walk or the elephant random walk with stop, we use the theory of martingales. So for example, I will explain you the second line. Sigma n is the sum from 1 to n of xk squared. So sigma n plus 1 is sigma n plus xn plus 1 square. So the conditional expectation of sigma n plus 1 given the past is sigma n plus the conditional expectation of this guy, but the conditional expectation of this guy is Pn. So it is 1 plus b over n sigma n. Okay. I will denote it here by beta n, sigma n. And so when you are in this situation, it's very easy to propose a martingale. And the asymptotic behavior of the martingale will give you the asymptotic behavior of sigma n. So I denote nn Bn sigma n, where Bn will be the product from 1 to n minus 1 of beta P minus 1. So the important thing is that Bn is Bn is beta n, Bn plus 1. Okay. So the conditional expectation of Nn plus 1 given the past is simply Bn plus 1 times the conditional expectation of sigma n plus 1 given the past. But we already compute this. It's Bn plus 1 beta n sigma n. But Bn plus 1 beta n is Bn. So this is Nn. It simply means that Nn is a martingale. So it's very easy to construct a martingale, for sigma n, and for Sn is exactly the same calculation. So very, very easy. Okay. So the idea now is to use the martingale theory, the one for Nn, for example, to deduce the asymptotic behavior of sigma n. Okay, so this is a calculation for Sn, the same as the calculation for sigma n, exactly the same. Okay, and this slide is a little bit more technical, but it's not so complicated. Why do I put this slide? It's to explain you that it's not so easy to say something for the elephant from the book with stops. Why? For Sn or for sigma n, the same calculation, okay? The conditional expectation of Sn plus 1 square given the past, you do the calculation. So the first term is Sn square, second term 2Sn xn plus 1 and xn plus 1 square. For the elephant from the mock without stop, xn plus 1 square is 1, so it's okay. But here it's not 1. So we already compute the conditional expectation of xn plus 1 given the past. It's a over n Sn, so you have 2a over n Sn square, and this last term is given here. Okay, it's Pn. So when I want to compute the increasing process of the martingale, I have to compute this conditional expectation. And after a very simple calculation, you obtain this quantity. And for the elephant from Bordeaux without stop, this sigma n is n, so this simplifies to 1. So here it's more complicated because of the sigma n. And okay, the free regime, it's easy to explain this, but what I want to say just before, that this sigma n divided by n at the power b will converge to a random variable. It converges to a Mittag-Leffler distribution. This is the reason why we will have to talk about the Mittag-Leffler distribution, and this is also the reason why it will be more complicated here. Okay, so what is the Mittag-Leffler distribution? Serious, very serious. You have the Mittag-Leffler function given here, and for alpha equal to 1, it is exponential. Okay. So you have many other Mittag-Leffler function with 2 parameter, multidimensional Mittag-Leffler, etc., etc. So, okay. A random variable has a Mittag-Leffler distribution if its Laplace transform is given by the Mittag-Leffler function. Okay, so it's simple. So the Mittag-Leffler distribution satisfies the Kalman condition. So if you can compute all the moments of a random variable and they correspond to the moment of the Mittag-Leffler distribution, which is given here because of that, you will be sure that your random variable will follow a Mittag-Leffler distribution. Okay. Okay. The probability density function is quite complicated. It's only simplifies in the case where alpha is 1/2. And otherwise, or if alpha is 1, but if alpha is 1, I think x is 1. Alpha 0, 1.
1 was the exponential.
If alpha is 1, x is 1. Yes. Yes, if alpha is 1, x is 1. Okay. Okay. So I have proved that the number of ones divided by n at the power b converges almost surely to the Mittag-Leffler distribution with parameter b. And I can tell you the story about that. I saw 2 papers with wrong results for the elephant from with stops. So I made simulations, and I saw that the asymptotic distribution of Sn properly normalized will not converge to a Gaussian. So after these 2 papers, I decided to write this paper and to prove this. My goal was to prove this, but perhaps I've lost too much time. If we will have time at the end, I will try to prove this or to give the ideas for this. This comes, why this is true, it's because of that. Okay. If you have a sequence of random variables where the increment, the distribution, the conditional distribution of the increments as a Bernoulli distribution with parameter Pn, which is a simple function. Here, it's a very simple function of sigma n. You will have a Mittag-Leffler distribution. Pn can be a little bit more complicated, and you will still have a Mittag-Leffler distribution at the end. Okay. Okay. So the result on the elephant from the mock we stop in the diffusion regime, the position divided by n goes to 0. And the asymptotic normality, you have to Sn, you have to normalize by the square root of sigma n and not by the square root of n. So So if you normalize by the square root of sigma n, you will have convergence to a Gaussian distribution. And if you want to normalize by the square root of n at the power b, you will have this mixture with the square root of sigma prime n, which is independent of the Gaussian and has the same distribution as sigma. Okay. You can also have law of iterative logarithm, quadratic strong law, etc., etc. Okay. In the critical regime, Sn over n goes to 0 almost surely, and you add a log as in many situations in critical regime. Okay. And in the superdiffusive regime, Sn over n at the power a converges almost surely to a non-degenerate random variable L. Kilian and Lucille have made a very beautiful work on the distribution of L for the elephant random walk without stop. With stop, it's much more complicated, but it will certainly be also similar result as without stop, but more complicated, I think. Okay. Now I have many times for the Ewens-Pitman process. So this is known as the Chinese restaurant process. So why do I study this? Because when I published this paper 2 years ago about the elephant random walk with stops, someone contacted me, Stefano Favaro, and because he saw Mittag-Leffler distribution and he knows very well the Chinese restaurant process. So he said to me, why don't we build a Chinese restaurant process, a mix of Chinese restaurant process and elephant random walk? Okay, why not? But so we propose an elephant random walk similar to the one before with a mixture of Chinese restaurant process, but was it really interesting? I don't think so. So we, I wasn't aware about all the literature of the Chinese restaurant process. So I look at the book of Pitman, and the proof there were very complicated and sometimes no proof at all. So I decided to try to find martingales and to better understand the Chinese restaurant process. That is why we work together on this process. But it is a very well-known process, and we thought all was already proven for this process, but finally no. And many things remains to be done using simple martingales. That's a strategy. So a customer arrives in the Chinese restaurant with an infinite number of tables. So he's set at the first table. So we are here. He's set at the first table with probability 1. Then a second customer arrives. So 2 possibilities. First possibility goes to the first table with probability 1 minus b over 1 plus theta. You can think of theta to be 0 if it's, and to a new table with b plus theta over 1 plus theta. And the process continues. At stage n, so we have k tables, and the customer goes to a new table with this probability. Otherwise, it goes to the other tables. Okay. And here we are interested in the number of tables. What is the evolution of the number of tables? Okay. So the total number of tables, I will denote it by Kn. And the table with exactly R customers, KRM. Okay. So Pitman, his book, I think many probabilists they have suffered reading his book. Jean Bercu told me he was in Saint-Flour when Ewens-Pitman gave his lectures, and he suffers a lot. Okay. So in his book, he proves that the number of tables divided by n to the power b converges almost surely to something related to the Mittag-Leffler distribution. This is the reason why Stefano contacted me, I think. And when theta is 0, KB0 is exactly the Mittag-Leffler distribution with parameter b, exactly. Okay. And the convergence also holds in Lm for any integer m. So when you read the proof in Pitman's book, he's making a kind of Girsanov change of measure. So he uses an exponential likelihood ratio for martingales. Think complicated, but it's much more. It's not really complicated, in fact. Why? Because the number of, what is the evolution of the number of tables? Kn plus 1 is Kn plus an increment, and the conditional distribution of the increment is a Bernoulli distribution with parameter Pn. The Pn is given here. You replace K by Kn, the total number of tables. Pn is theta plus b Kn divided by n plus theta. So you can adapt the technique I use to prove that Kn divided by n at the power b converges to something related to the Mittag-Leffler. Okay. And the martingale is not so complicated. It's the same as before. When theta equal to 0, we recover Bn. Nn was Bn times sigma n. And here is exactly the same. And the proof, very simple. Okay. Okay. So now I want to talk about a beautiful paper of Hyde, 1977, about martingales. In many situations, the evolution of the martingale is given by the evolution of its increasing process. And the increasing process divided by n or by a rate, a deterministic rate converges to something. Something can be deterministic or random. When it's random, it's more complicated. But okay. So now we are in another situation where the increasing process of the martingale converges, which, and for example, if a martingale is bounded in L2, the increasing process of the martingale converges. So what can we say? What can we say? It's so we can say something. Vn is a kind of remainder of a series, so it goes to 0. So when you divide it by something which goes to 0, if it converges to a limit, and if you have a Lindeberg condition, this will allows you to say something like this, the blue thing. Okay. And for the Chinese restaurant process, we are in this situation where the martingale converges, is bounded in LP for every P. So we can say things like that. So we have shown that the number of table minus n at the power b times the Mittag-Leffler divided by Kn converges to a Gaussian, and also this result. Okay. And the situation is more easy for KRN. For KRN, you have this kind of result. No proof in Pitman book, no proof at all. It gives a result without proof. But it's like 4 or 5 pages to prove this. It's not straightforward. When R is equal to 1, so you are looking at the number of tables with only one customer. For L is equal to 1, PBR is simply B. Okay? So Kn over n at the power b converges to kb theta. K1n over n at the power b converges to b times kb theta. So you have for free consistent estimator of theta, which is a ratio of K1n divided by Kn. So if I denote by b hat n K1n divided by Kn, I have for free an almost sure a strongly consistent estimator of B. And using the result of Hyde, you can prove that the square root of Kn times b hat n minus b goes in distribution to a normal random variable with 0 and variance 1 minus b. So very simple. You have a paper of van der Waart with a non-explicit estimator of b, argmin of something. Here it's for free. Okay. Okay. What about large deviations? A long time ago, Feng and Hoppe, they have proved that Kn over n satisfies a large deviation principle with a rate function I given here. It's a non-explicit rate function, but LT is explicit and is given here. Okay. So 2 possibilities. I explain you how to prove this, or I explain you the convergence to the Mittag-Leffler distribution. As you want. Tell it to me because so we prove this. It's a paper in progress, and we prove this result with a technique totally different from the one of Fang and Hope. And with our result, you can prove also concentration in exact concentration inequalities, the sharp concentration inequalities, I will say. And we are trying to prove sharp large deviation principle, but it's more complicated. So what do you prefer? Okay, okay. So I don't know if you were at the talk of Jean Bertrand. He used the same. I call it the flageolet calculation. He used the flageolet calculation to prove this. It's a very powerful calculation, and for me, it's a beautiful. It's a very flageolet calculation is really beautiful. So Kn plus 1 is Kn plus sigma n plus 1 plus Cn plus 1, where the conditional distribution of Cn plus 1 given the past is a Bernoulli distribution with parameter Pn. I will focus on the case theta equal to 0. Otherwise, it's a little bit more complicated. So Pn is, before it was n plus theta, adenine B Kn, I don't remember exactly, but now it's simply this. Okay. So I denote by Mn of T the Laplace transform of Kn. Kn is always smaller than n, so this is finite, no problem. Okay, and so the important thing is in the flageolet calculation is the generating function of the Laplace transform. So it's sum from 1 to infinity of Mn T Z n minus 1 Z belonging to C. We will have a restriction for Z, but okay. Okay, so I want to compute this. Do I have done like this? I don't remember. Yes. So this is Kn plus Cn plus 1 given the past. So but this is simply a Bernoulli random variable with parameter Pn. So it's 1 or 0. It's 1 with probability Pn, or 0 with probability 1 minus Pn. Okay, but Pn is this quantity. So, okay. So I take this one plus I put Pn here. Okay. I just put Pn and -1. It's correct, okay? So Mn plus 1 is, so I compute I use the Tor property of the conditional expectation. So Mn plus 1 is Mn plus 80 minus 1 Pn. Okay. But Pn is this. So it's Mn of T plus you have a B over N An. So this is a derivative of Mn. So it's Mn of T. Perhaps I will erase the top. So Mn plus 1 of T is Mn of T times B over N with T minus 1, the derivative of Mn. So now I want to compute the derivative of this function. So sum from 1 to infinity, Mn of T. So the strategy is to obtain a partial differential equation for capital F and to solve it using the method of characteristics. And here it's possible to do it. Okay, so it's the sum from 2 to infinity. So N minus 1. Okay, so it's sum from 1 to infinity, Mn plus 1 times N. Then, okay. So you can ask, why are you computing, why are you calculating complicated things? Because you just need the Laplace transform of Kn. You just need, but in fact, you see the problem at the top, and if you are able to compute this, you will have very sharp result on this term. So this is why it's important to compute this. So, but we saw this equation here. So you plug this term inside this term. So, and you make the calculation. So it's the sum from 1 to infinity, half time, I think. N Mn of T Z n minus 1 plus, and the important term is this one, which will be simplified by this one. So remember, if you have n plus theta here, it will be a little bit more complicated, but you can do it, but more complicated. Here we don't have, so this simplifies with this one, and you will have be 18 minus 1, the sum from 1 to infinity of m prime. Okay. So this is sum from 1 to infinity. N is n minus 1 plus 1. Plus b 18 minus 1. And this is the derivative of okay. But what is this term? This term is Fn. So you will have, thanks to this equation, you will have d f z over dz is f of t and z plus n minus 1 mn of t z. So this is this term, but you have to multiply it by z. So it's z b over dz plus b so you have your partial differential equation. F T Z is 1 minus Z okay. And now, if you are lucky, you use the method of characteristic and you can solve this equation. And we are lucky. And the solution with the method of characteristic is not so complicated. Is F T Z 1 minus 1 over where Tt is 80 over 80 minus 1. So it's very simple. It's very simple. And I will finish with this. But using this now, as Ft and Z is the sum from 1 to infinity of Mn Z, you will have from this a very sharp result from this one. And for example, I skip the details, but Mn of t, Mn plus 1 of t is simply 1 over n factorial, the integral of, after some calculation, no? Which are not really complicated. where this is a Mittag-Leffler function. So you have many results on the Mittag-Leffler function. And thanks to the result on Mittag-Leffler function, you can prove that the limits of 1 over n log of mn of t is minus log. It's related to this term ct, 1 minus simply that. And this is enough to prove the LDP. From this, the limit is well defined and is so using Gartner-Ellis theorem, you directly have the large deviation principle. Now, using this, you can also have sharp concentration inequalities. But I need very precise results on the Mittag-Leffler function. And it's not easy to find very sharp results on the Mittag-Leffler function. You have books, but with many parameters, 2 parameters, etc., etc. But very sharp result. Okay, I'm done. Yeah.
It's important to remind us of the notation P and R. So
yes,
the number of tables with customer, R customer.
Exactly. Yes.
Can you say what the large deviations for that?
No result. So no, it's not totally true. Stefano Favaro said to me that he wrote a paper on large deviation principle for KRM, but he thinks the result is not true. Sorry. So large LDP for KR, you can prove it. We have all the material to prove it, but we are more interested in the couple KN, KRM, because with the couple, you will have an LDP for the estimator of B using the contraction principle. So we are working on that. I think it's also possible to have LDP for the whole vector, but it's more complicated. Yes, yes.
The other question I had was for your Prof.
Yes, yes. No. Good question, very good. We have this kind of partial differential equation. We are not able to solve it. And I can write it down, but I think we know what should be the solution, and we know what should be the rate function for the elephant random walk, but no. So it's an open problem without stop. Without stop, LDP for the elephant random walk without stop, no result. So it's a very good question. Yes. 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 The first question, I think they are not really physicists. They are mathematical physicists. Schulz and Trimper. They said the motivation was to propose a random walk knowing all the past, all the history, and with a parameter that change the behavior of the random variable from diffusive to super diffusive. After that, many papers were written by physicists on this elephant random walk, but very few papers in mathematics. But Jean Bertrand made the connection between the elephant random walk and the polyions. And then now you have like perhaps 100 of paper from mathematics on the elephant random walk. For your second question, there are many connections with genetic, but I don't know really the topic, but many connections with genetic, population genetic. Yes, it's useful. It's not just for fun. No, but it's, I think it's really useful in Bayesian statistics also. It's useful. Yes. Yes.
If theta is 0, so
yeah.
Also for theta
you have a perturbed PDE. For theta different from 0, you can make a change of measure. We have a PDE, but difficult to solve it. But in fact, if you make the change of measure, you will obtain an exact form for this when theta is different from 0. Yes, exactly. Yes, exactly. And you have a closed form, not so complicated, but more complicated, a closed form for F when theta is different from 0. And a funny thing is that in the paper of Fang and Hope, they prove the LDP for theta equal to 0. And for theta different from 0, it's 3 lines, 4 lines. What? So the arguments are really not clear. What you can see is here, this does not depend on theta. Even for theta different from 0, the limit of the Laplace transform will not depend on theta. So you have an LDP which will not depend on theta. But if you want to prove sharp large deviation, you will have a prefactor depending on theta. Yeah. Yes, you have. No, B is not 0. B is R. When R is 0, this is your question, or R is different from 0? R is different from 0. For me, R is different from 0. Yes, you have. Okay. I don't know. I don't know. Good question. I don't know. I think it's probably possible, but you have this sigma n, so the normalization is random. So I don't know. Okay. Thank you very much. Thank you.